This session is a continuation of the Chapter 5 review with problem 23. In this problem, it says write a coordinate proof. Coordinates of vertices of quadrilateral OPQR are given. Prove that triangle OPQ is congruent to triangle QRO. So, in order to prove that this triangle is congruent to this triangle, things don't change in coordinate proofs from a standpoint of what you're trying to do. What changes is how you're going to do it. And sometimes coordinate proofs can be actually easier than other proofs. In this case, we have only a few tools to work with, because in a coordinate plane, we can't really work with much in the way of angles, except when it comes to right angles. And in here, we're not really going to be concerned with right angles, because what we need to find, it appears, is we're going to try and use side, side, side theorem. So what we need to do is to find that side RO is congruent to QP and QR is congruent to PO. Now the way we're going to do this is we're going to use the distance formula. Yes, the distance formula. Something that you should be very familiar with at this point. So I'm going to write the distance formula up over here so that we can refer to it. So distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so first let's try to find the length of RQ. Let's do RQ first. So we'll do it right here. So RQ, and RQ will be the difference of the h's. So it's h minus 0 squared plus the y's, which is k plus j minus j squared, and we take the square root of that whole thing. So to simplify this, we have h minus 0 is just h squared plus k plus j minus j. The j's cancel out, and we're left with k squared, and we take the square root of that. Alright, now let's do PO. So PO is going to be h minus 0 squared plus k minus 0 squared. K minus 0 squared, and we take the square root of that whole thing, and then h minus 0 squared is just h squared. K minus 0 is just k squared, and we take the square root. Okay, at this point we have RQ is h squared plus k squared square root, and PO is the square root of h squared plus k squared. They're the exact same value. So we've just shown that this side is in fact congruent to that side. Now let's do RO. And RO is moving along the y-axis, so we can use just the ruler postulate, which is simply the difference of the y-coordinates here. So RO is j minus 0, which is just j. And then we're going to do QP, and QP, again using the ruler postulate because it's going up and down vertically. You can see that the x coordinate is exactly the same, it's h, so Q is directly above P. So it's going to be the difference of those values. So we have k plus j minus k. That's a minus sign. Well, k minus k, those cancel out, and that's just j. So here we've shown that RO is j and QP is j. So now we know these two sides are the same, and we know from our standard geometric principles that QO is congruent to QO because of the reflexive property of segment congruence, and therefore triangle QPO is congruent to triangle QRO. You could have used the same congruent statement, but it really doesn't make any difference at this point. So we just proved those two triangles are congruent using a coordinate proof. And so you can see that even though it's a little bit more messy than a two-column proof, it sometimes can be a little easier because it's a little more free format. So now on to problem 24. Okay, in problem 24, it says place an isosceles triangle in a coordinate plane in a way that is convenient for finding side lengths. Assign coordinates to each vertex. This may sound like a silly question to ask, but it makes a big difference in how you place a figure in the coordinate plane to make it easier or really hard for you to figure out how long the side lengths are. So let's go ahead and put up a coordinate plane, and then let's go and create a triangle. In this case, we shall make a blue, purple, pink, whatever that is, triangle. And notice where I put it. I put the vertex of the isosceles triangle right on the y-axis. What that does for us is it allows us to take advantage of the fact that the vertex is going to be a perpendicular bisector of the base of this isosceles triangle. So this distance and that distance are exactly the same, and there's a relationship with these distances. So to put in the coordinates, then we would have over here, this coordinate is going to be 3, 0. And this coordinate is going to be negative 3, 0. And then this coordinate would be 0, 6. Making it nice and easy to find those lengths. Now if I wanted to assign generic coordinates to these points so that it didn't matter where I placed it, this would obviously be the x coordinate, 0. This would be the negative x coordinate and 0. And this would be 0 and a y coordinate. Okay, now let's move on to problem 25. Problem 25 is our last problem in this review, and it tells us a rectangle has the vertices 0, 0, 2k, 0, and 0k. Find the fourth vertex. So we're going to have to use what we know of the properties of rectangles and coordinate proofs to find this fourth coordinate. So the first one is fairly easy. I've anticipated a graphical solution to this. So the first coordinate is 0, 0. So let's go ahead and put a point at 0, 0. So there's 0, 0. And it says 2k, 0. Well, k is going to be the y coordinate. So what they're trying to say is that I want the width of this triangle to be twice the height. So it doesn't really matter where we put it. Let's put it so that it's out here at 6. So we'll say that 6 is 2k. So put that there. And that makes this point 0 and just k, which is going to be half that distance. So that's going to be at 3. And now you can clearly see that our fourth coordinate is going to be sitting right here. And let's go ahead and write in our vertices that we've got so far. So this is point 0, 0. This is point 2k, 0. This is point 0, k. And this point is obviously going to be, it's going to have the same x coordinate as this point because it's directly over the top. So this is going to be 2k. And it's going to have the same y coordinate as this. So it's going to be 2k, k. And that gives us the coordinates of our rectangle. And I suppose just for kicks and grins, I could try to put in a rectangle here, and I'll probably end up messing up my entire drawing, but let's give it a shot. So here is a rectangle, and let's go ahead and make it that color. And there we have it. And that is problem 25 in the Chapter 5 review. And I will see you next time.